can start when you want.
Okay. And I will disable my camera, but can you do this with
Yes, yes, I can turn off your
the
camera.
Zoom window disappear? Okay. So welcome everybody. This is lecture 2 of the this crash course on reinforcement learning. I know we have at least 2 new people today, so this is uh, the slide is a suggestion of or reading, some reading that you can have in order to delve deeper in this topic. This is the textbook, and this is a video course, and these are the first 2 resources that I suggest reading and listening and looking at. This is a very advanced course, including also deep learning, not only reinforcement learning. And this is just 2 hour video, 2 hours video, just as an appetizer, a tutorial. And this contains solution and implementation, the code for the exercises proposed in the textbook. Okay, this is the second lecture that is on the case when we don't have the model. I try to recall you something about yesterday. We have this decision problem. We have some, maybe I can show you in this as usual, in this example. So we are concerned with this kind of problems. This is the graphical representation. These are the states. This is a state. From a state, I can choose one action or another action. I can choose several actions. And according to the action I choose, then something can happen. Here represented from the graph going in this direction, landing in this state, or going back to the original state. And what happens here is not under my control, will happen under certain probabilities. Here you can see that with 80% of probability, I will have a reward of +10, and I will go back to the state A. And with the probability of 20%, I will have a reward of +3, and I will land in state B. We have our problem means solving our problem means that we are trying to choose the action in order to maximize the expected value of the return we are receiving in a trajectory, not only in one choice, of course, but during several choices. All of this takes to defining a value for states. For instance, here, the value of the state A would be the sum of every reward you can obtain. If I start, let's use already the notation with the stochastic variables. If I start with the state the value of the state A is the sum of all the return I can obtain in a trajectory starting from state A. So I will write this way. I have the starting point, which is the state A at time t, and then I can take the reward I obtain immediately, and then the reward I obtain at step 2, and so on. And then there is a discount factor because I'm less confident in rewards which are far in the future. All of this I take this way, and I take the expected value of all of this. So in this way, I have a value for every state. And if you have looked at the previous lecture, this value saying which reward I will obtain at step t+1, t+2, and so on, depends on a policy. That means a policy is a distribution over actions conditioned on states. So in this case, I would get the action from a probability distribution between this distribution over every action which is possible from the state A. So in this case, I need, in order to make a trajectory here, in order to make an episode, I need a way to choose when I'm state A, which one of the two actions I'm going to perform, to act. Okay, so our problem is the computation of this value function. But in order to compute this value function, this is a expected value containing the policy, but also these probabilities. So in order to compute exactly this value, I need these probabilities. These probabilities are called model of our problem. The problem is called Markov decision process, and the shortcut is MDP. Okay, so we are now in the case that is called model free. Model free case means that we don't have the probabilities. We do not have P. Okay, so no, we cannot do an exact computation of expectation when P is involved. That means of expectation in this problem. And why are we concerned with model-free problems? Well, I have a bad news. The world, every problem in the world is model-free. If you think to real-world tasks, here I listed several of them, but some of them I would say, all these tasks are characterized by the fact that you don't have the model, but usually you can sample experience. In other cases, maybe in the game of Go, in a deterministic game, maybe assuming a fixed opponent, the game is deterministic, means that you know the rules. This means that you know the model, but the model is so big in the case of Go, the model, the dimension of the model, we can tell the dimension of the state space. The state space in the game of Go is more or less 1 to the power 10 to the power of 150. So this is a very huge number, and you cannot use this number for the tabular reinforcement learning that we talked about the day before yesterday. Okay, and in some case, I don't know, in an helicopter, you of course you know the dynamics, you know the physics law giving this how the helicopter is flying, but you cannot use this model. I mean, this is a very complex dynamical system, but you can simulate trajectories, you can build a model, you can build a simulator, a software, and you can do samples. Okay. Now, remember the general setup of yesterday. Prediction, improvement, and all of this in a cycle which is called control cycle. Okay, this is what we are going to do always in reinforcement learning. And this cycle, under certain hypotheses and conditions, will give you a good approximation of the optimal policy. Now, we don't have the model, okay? We studied how to do the prediction and the improvement using the probabilities P. Now we don't have the probabilities P, so we have to find new ways. Well, since we have samples, the first thing comes to mind, I guess, is making a Monte Carlo prediction. What does it mean? Monte Carlo methods are methods that can estimate the value of the state, the one I was talking before, via samples of the return. That means exactly, we do an episode up to the end, we see how much we earned, how much is the total reward, the return, and we do this several times, we average, empirical mean, I mean, and then by the law of large numbers, we have a good estimate of the value. So I try to spell this here. Let's take everything away. So with Monte Carlo estimates, instead of saying I'm here, I see what happens when I do action 1, meaning that I know that the probability of having 10 is 80% and the probability of having 3 is 20%. This I don't know. Okay, so forget these numbers. So the only thing you can do is, okay, I have a policy that in A choose 1 and in B choose 1. Okay, let's say the policy is fixed. The policy is deterministic and policy of A is 1 and policy of B is 1. What is the value of this policy? What is the value of this policy? This is the question. Well, just apply the policy, choose 1, let the environment answer, and then sometimes you will land in B, sometimes you will land in A. Let's say in this moment you go here in A, you reapply 1. Let's say now B happens, you apply 1 according to your policy, you go here. Let's say that this time the environment is taking you here, you reapply 1. Let's say that this is happening, you reapply 1. Let's say this is happening. I just described an episode that could be synthesized this way: A1 plus 10, and they said A, then again 1, then plus 3 happened, and then B, then I choose 1, then plus 42, then A, then 1, then plus 3, then B, then 1, then plus 1, then the end. Okay, I think this is the episode I was describing before. Please interrupt me if I'm going too fast. Today we have a lot of things to say, so I will try to go faster, but please interrupt me. Don't sacrifice comprehension, understanding for speed, please. So this is the episode. From this episode, I would compute the total return. That would be 10 plus 3, 13, 55, 58, 59. So the total return, what I call the G, would be 59. Okay, I'm not using a discount factor, otherwise I have to put also a discount factor. And then I would say, okay, my estimate for the value of the state A is more or less 59. Okay, let's say now I do another episode, A1 and so on. Let's say I obtain a total return of 42. Then now I would say that the value of A is, somebody tell me, what is the my new estimate of the value?
The average between 59 and 42.
Exactly. I mean, it's very intuitive, right? And of course, there is some theory, some theorem behind that tells you that if these estimates are independent and identically distributed, which they are, then this empirical mean will converge exactly to the expected value of the episodes, which is by definition, if you think about it, exactly the value that you're looking for. Okay. So what I'm telling you is this one. So I just told you this slide, but let's point out the formalism. So we don't know the model, okay, this is clear, but we can sample episodes of experience. Sampling episodes, remember, always is under a policy. Sometimes I will not tell you this. I do an episode has no meaning if I don't assume that I'm choosing actions according to a certain policy. Okay, according to this policy, I obtain this sequence of reward states and actions chosen by me. And this is the notation I use to denote that these episodes are taken according to this policy. Please note that here I should say also according also to the model, okay, the unknown model, but I'm not saying this because I have not any control on this. So I'm just specifying that I'm choosing this policy to choose actions because this policy is the object that I'm going to modify in the improvement phase. Okay, please take care. Here we are in the prediction phase. So I have just a policy and I need to estimate the value of the state, which is by definition this expected value. So I can use this sample as an estimator of the expected value. And in common language, I mean in statistical language, this estimator is unbiased, means that the expectation of the sample, the empirical mean of the sample under, not the empirical mean, I mean the expectation of the samples under the probabilities that we don't know, but if we could know the probability of every episode, that is a joint probability by the policy and the transition probabilities, then this expectation would be by definition exactly the value that we are estimating. This is the definition of an unbiased estimator. But remember, this is an important point. Monte Carlo estimates have high variance. Why? Because at every time step, we are doing a step. So let's see this here again. Whenever I take a step, the reward I obtain, I take one step and let's say I obtain this reward. I obtain plus 10. And this reward can be very different from the expected reward I could obtain from the state. For instance, the expected reward here is 0.8 times 10 plus 0.2 plus times 3. And this is different, of course, from just 10. And sometimes something very, very different from this expectation can happen. Let's say this is 8.6. Okay, in this case, it's not very different. But when something else happens, if I obtain 3, then my estimate of the value of the state up to now is 3 plus the value of the other state. I'm in the starting point where all the estimates are initialized to 0 maybe. And so you can see the variance can accumulate. The second time when I land in B, I can obtain, I don't know, from 1, 39 or 42. Okay, I can terminate the episode obtaining just one, and this one is very different from the other two rewards, which are similar and that are happening with a total probability of 8% of 80%. Okay, so the variance is accumulating while I'm doing the trajectory, the episode, and at the end I will have a very, very large variance. Okay.
Excuse me, just a question.
Yes.
You said that is an unbiased estimator because I know that the final state is the absorbing state.
Okay, Monte Carlo can be used only when there is the absorbing state, because we need the episode to terminate to have the sample, right?
Yes, so I know that it's finite, so I know which is the state I will finish.
Yes, you finish. You have a value, and this value is stochastic, right? And there's a probability of happening, right?
Yes, I have a high variance because I don't know the reward, but I know that I will finish there. So it's unbiased.
No, I mean, you're asking why it is unbiased, right?
Yes.
Okay, so the definition of unbiased is that if you take the estimates that you're doing and you weight them by their probability of happening, that in this case means taking the expected value of RT plus 1 plus RT plus 2 plus and so on up to the end. Okay, under, let's call these episodes tau, and these episodes are taken with the probability. This probability is a probability given by pi and p, but in a very complex way. Okay, and if you take the expectation under this joint probability, then the estimator is unbiased if this expectation is exactly the value that you're trying to estimate. Okay, what is the value that you're trying to estimate? The value is the value of the starting state. Of course, the starting state is the initial one here. And if you think about it, this is exactly the definition. This is the definition of value of the state S. I mean, this.
Okay.
This thing here is exactly this one.
Okay.
Okay, so of course we need the episode to terminate, but it's not.
The expected value of the estimator is exactly the estimator itself.
Exactly.
Okay.
This is the definition of an unbiased estimator.
Thank you.
Okay, this is a good property. I mean, because it means, okay, it is very. I mean, I just choose these samples, and eventually I will get as close as I like to the value I want to estimate. But due to the high variance, you will need a lot of samples to reach a good approximation. Okay. And there is another thing that we need to point out. Remember in the last lecture, do you remember how we were estimating the value? Let's try to remember because it's useful. Tell me the Bellman equation for the state S. Or I mean, I can tell you, I can help you, and somebody answer me. And I will help him in answering. Please, a volunteer. Don't be shy, don't be scared.
So first the expected reward, right, for the next step.
I can't hear you. Speak louder.
So I was saying first the expected reward, so for the next step,
Okay, so I'm asking you the Bellman equation. I can show you on the usual picture. So we are in this state. Okay, the Bellman equation was the recursive equation for the value of the state. And it was this way. First, I need to choose an action. Okay, so you choose the action with the probability. So everything will be weighted by this probability, right? And then I have something here to multiply. Now I have this action. Let's say I'm here. What happens? What can happen?
So the probability that under the action I go to state A or state B. So
exactly. So I can have 3
so the sum
or I
over
can
the
have
states
10.
that I can possibly reach. So the sum over the states that I can possibly reach from there, weighted by the probability.
First go look at the reward. So we will have the sum of the reward with their probabilities, right?
Yeah.
So I will have +3 times 0.2 and so on, +10 times 0.8. I mean, I will have the expected value of the reward. This is something that we called with the tabular notation, the expected value of the reward from the state S doing the action A. I don't know if you remember this notation.
Yeah.
Okay, and then go on. Now we are in a state that is B or A, doesn't matter. Or I mean, it matters because we must wait for the probability of happening. So we land in a state S prime. In this state, there is a value. But what is the probability of landing in the state S prime?
So P of S prime given A and S. The probability of landing there given we were in state S and
yes, the probability is the probability of landing in S prime starting from S. And this probability, remember, is given a certain action A. This was the notation, right? And then we have to sum over every state that we can reach. Okay?
We have also to add the discount factor in front of the summation.
You are right. So, okay, well. Okay, you understand.
This is sum over the actions, right, that we can take from state S.
Sorry? Plus gam S prime.
So this is given that we have taken action A, but we should sum over the different actions A over the quality. Right?
Yes, perfect. You are right. Very good. So this is the Bellman equation, okay? You see it's very intuitive. I mean, seems a strange formula with summation and so on, but it's very intuitive if you have the picture in mind. But what I want to point out is that you are doing just one step. One step. You are not doing an episode. Is that clear? I'm looking just at the first reward. And after that, I will say, okay, since I land in the new state B, the next on my return is estimated by my estimate of the value of B. Okay, so I'm using this estimate to change the value of the estimate of the previous state. When I do this, I say that I do bootstrap. Okay, the methods we learned in the first lecture are methods with bootstrap. Methods with bootstrap are good in a certain way, but have a problem. They introduce a bias. The bias is the initial value you give to the states. Unless that initial value is the correct one, that initial value is a bias that will always stay there. Okay, so bootstrapping methods are biased, different from Monte Carlo methods. In Monte Carlo methods, we have no bootstrap. Why? Well, because here I'm not assuming an estimate of any intermediate state. When I stop, I reach the terminal state, and I assume that its value is the correct one, that is 0. Okay? Terminal states are the states where I know the value. Okay? So, Monte Carlo method is with no bias, high variance, no bootstrap, and another terminology we need to learn is that is a method that you can't apply online. You can't apply in real time. I mean that you need to wait for the end of the episode. Okay? I have to check if doing this move in a game of Go is going to produce a good or a bad result. Well, I will try, and I will wait till the end, the result, to check if that move was good or bad. Okay, this means that I can't apply in a real game, in real time. We say in this case that the method is offline. And this is usually a bad thing for a method. We like to have methods which are online, which can be applied in real time. Okay. Now, computing the empirical mean just by summing all the reward we obtain, all the return of the episodes. Remember, the Monte Carlo methods means I'm doing a lot of episodes and then I'm computing the empirical mean. Okay, if these are the return of the episodes, the empirical mean is this one. Well, there is a recursive formula for the empirical mean, which is this one, that gives you the last value of the estimate just using the last result and the previous value of the estimate. Okay, this is a common formula. I assume that you know it. By the way, in the exercise part, I ask you to prove it, but it's very easy. You just write the two parts of the equation. And in the Monte Carlo methods, this formula gives you this algorithm. So think to this algorithm how this is working. It's very important. I start from a state S and I start an episode. So this means that this is S and I take an action according to my policy and I see what happens and so on. Okay. By capital T, usually we mean the terminal time, the stopping time when the terminal states happen. So ST is the terminal state. And now I look at every state. In every state, I have a return. Okay, this is important. Maybe it's not evident. When I do an episode from S, the total sum of the reward is the return of S. But if I start from the second state, the partial sum of the reward from that state on is the total return for that state. I mean, when I do one episode, I'm actually doing several episodes, just starting from different states. Okay? And in this way, I can count how many times I visited the states. Is this clear? And this second line is just this formula here. That means this is the empirical mean of episodes. Okay, so now I have a table, I have a vector storing for each state I visited during the episode, the empirical mean of the total return obtained up to that moment with episodes. Please ask questions because this part is very important. I don't want to go ahead.
Yes, I do have a question. So I got the empirical mean. So the second element here, I didn't get the first one. So basically we were saying
this one.
Yes, exactly.
Okay, this is just an iterative way to count how many times you visited this state.
Okay.
Okay, every time I visit the same state, the point is that ST is the same year and year.
Yes.
Okay, so when you visit the same state, you increase this counter.
Okay.
And this is the denominator year, that is this K year.
Okay. Yeah,
okay.
Makes sense.
Okay.
I have a question if I can.
Yes.
So if, for example, if we start from one state, then we go on till we reach the terminal state. But in the meantime, we visit again that state. Are we going to count it twice? So can we look at like the reward from the very start from the middle point? So this will be two different numbers. The second would be, well, lower or higher. Well, it depends if we have negative.
Very good question. Thank you for asking. The answer is you can do in both way. You have two different algorithms. The first one is called the first visit. The first one is called first visit, meaning that I'm counting only the first visit, and the second one is called every visit, the one you are proposing, right? But are you asking this because you can see a problem in this case?
Not yet. I was just thinking of this trajectory, so really came naturally if we came back. Wasn't thinking.
Well, okay, of course, every visit is more tempting, right? Because you are updating the value more often, and so it is quicker, probably, right?
Yeah, so you have more samples really for the same state.
Yes, but the second sample is no more independent from the first one.
Oh yeah, sure. Yeah.
Goodbye low large numbers.
Yeah.
Okay. By the way, this works very well. It converges eventually for different reasons, not the low large numbers, but it can be proved. But good point pointing out. These are different algorithms. If you want to prove that both of them works, you have to do different demonstration, different proof. And the algorithm that everybody uses, of course, is every visit because it's easier, it is quicker, and it works anyway. Okay, thanks for pointing out. But this is very, very important because you see how many details there are here that I'm not telling you. And if you want to check if one detail works and the other no, you probably have to do an experiment or try to prove it with theoretical tools. Now, follow me because we are going away from this very safe path of low or large numbers and so on. First, sometimes it can be useful to track a running mean. Running mean means that I don't trust the old episodes very much. Because I mean, if I'm doing episodes, I start now. Every episode take 1 day, and in 100 days, I will have 100 episodes of experience. After 100 days, maybe what happened 100 days before, I mean, it's no more accurate. Something changed, and so on. There are several reasons why you could need not to trust very much older episodes. One way of doing this is using this update formula. Look at this formula. It's really extremely important. It's the same as before. Only difference, this one was 1 over k. Okay, 1 over the number of visits of the state. What is the difference in putting this? This means that the weight you give to the last episode is alpha, but the weight you give to the second to last episode is alpha times, if you make some computation, alpha times 1 minus alpha. Anyways, of the order of alpha squared. Okay, so it is an exponentially weighted average. This is called, I guess, exponential moving average. Moving average is when you choose a window and you move this window and you look at experience only in that window. In this case, the window is always the whole window of episodes, but you are weighting the very last episodes with a very small number, the very small factor. Okay. Is this clear up to now?
Yes.
And I want also to tell you this. So we have now this update rule. The value of this state will be updated by the value of the state plus this. Or was the minus the value of the state. Look at this. I'm saying, assume that the value of the state, and put also some index here. This is the value at step, let's say, k plus 1, and this is the estimate you have at time k. Okay. Usually you don't put this index because you replace the values in place when you do the code. So this new value is really the same as before, just replaced. But look at this. I'm saying, okay, let's say that the value of the state is 42. I do an episode and I compute the new return. I make an episode, a sample, and the total return, this is, remember, the expected value of the total return. The total return becomes 50. Okay? Oh, my God. So I was wrong. 42 is wrong. The true value is 50. No, not this way. Maybe 42 was not really wrong, but you have evidence that the value 42 should be, in some sense, moved towards 50. So it makes sense to choose a value between 42 and 50. Okay? How much do you trust 50 to be close to the true value? This depends on alpha. So you just formed, this is, we call this the target. This is the old value. And you simply move 42 plus a confidence value, that is this weight, this is the learning rate called in the learning setting. And then you take the error, that is how much your new estimate change, how much it is far from the original value. This is called the error. Okay, so remember this language, it is fundamental. Reinforcement learning means that I'm computing a target and I will update my estimate with the variation, with something depending on the target. That means depending on the error that the old value and the target gives to you. Okay, and how much you are moving is given by this learning rate. I mean, it's very intuitive, right? Is this clear, this language, target and error?
Sorry, just to have a comparison with the formula you give above with 1 over n of st. In this case, you would have updated the 42. For example, you could have had vkst plus 1 over the number of time we visit a state in the episode that gave us the 50.
Let me check if I'm understanding. Let's say that st was equal to s. So the starting state was s. Okay.
Okay.
And you need to take count of how many times you visited s. So let's say up to this moment, nk of s is 21, because you made 21 episodes up to now visiting s. Okay.
Okay.
And then in this case, this is episode number 22. And so this alpha would be 1 over 22. Is this your question?
Yeah, and also during an episode, you could have visited the S more than once.
Okay, this is counted for in this notation. When I say nk of s equal 21, it means that I visited that state 21 times.
Okay.
That it means I counted 21 returns for this state.
Okay, and just the last thing, I was getting confused about with the notation, why we have GT this time. And in the formula you gave before, there were G1 with the 1 up, let's say.
Yes, it's sort of confusing. This is a general formula. The GR, I mean, this is given a sequence of returns. Okay, these are the number, these indexes for the episodes.
Okay, exactly.
Okay, and I'm assuming that all these episodes, let's say, are starting from the same state. Okay, so this key, the number of episodes is also the number of times I visited that state. I'm also assuming in this that I'm not visiting the same state in one single episode again.
Okay.
Okay.
Okay. Thank you.
Okay, so just to show you the code. As usual, this is the pseudocode. It's not a real language, but it is a pseudocode very faithful to standard imperative language. That means that the algorithm I'm talking about is really 3 lines. Okay, it's one cycle with 3 lines inside. This is the incremental computation of the return. This is the incremental computation of the number of visits. And this is the formula for the empirical mean. And of course, if you want to change this with alpha, you just take away this line. You don't need this anymore. And you change this in alpha. Okay. With alpha, I don't know, it was called constant alpha algorithm. Alpha algorithm. And Monte Carlo algorithm, of course. Questions? Okay, so Monte Carlo methods are very, very easy, okay? And I feel we said enough. Let's go to temporal difference prediction. These methods are more similar to previous lecture. Yes?
So in practice, the discount factor is applied only if I return in a certain state.
The discount factor is contained here. This is the total return. Also, yes, it is here, you see?
Okay, but it's applied only if I return in a state. So at the first return is gamma, at the second return is gamma to the square, etc. Is correct?
I don't understand the question. I mean, the cycle, maybe it's not clear. The cycle is going from the end to the beginning. Okay. And so at the end, you will have the last return, which is 0. And every time you multiply by gamma, so going backward, the last return will be multiplied by gamma square, and then gamma to the power of 3, gamma to the power of 4.
Okay, but okay.
Is this the question?
Yes, please.
Okay. Okay. Just a comment for us mathematicians. It can be difficult at the beginning to grasp that this code, for instance, is the same as the formulas I'm showing you here. Okay, because it is just an efficient way to implement things. It's a very natural way once you start programming. For the moment, try just to get the intuition. Okay, this is something that if you take 10 minutes by yourself or your time with a cup of tea, hot cup of tea possibly, because today is very cold, then you understand immediately. Okay, and it's very clear. But now we are probably going too fast for these things for mathematicians, but I guess the idea is clear, right? You are multiplying recursively by the discount factor several times, and since you are starting from the end, this means that the last reward will be weighted, as it must be, by several powers of the several factors of discount factor. Okay.
Sorry, I have a couple of questions.
Go.
The first is, with this code, are we calculating the value of v for all the states at the same times?
This is an every visit algorithm. Yes, you see, ST means you see at the beginning I say generate an episode.
Yeah.
This gives you every S0, S1, S2, and so on, and these are these ST.
So we are calculating the value of v for all the states contained in the episode.
Okay, the right language is visited in the episode.
Okay, yeah. And so I don't get why instead we update the value of n for at each iteration. Why are we not updating only if we visit that state? I mean, the state we started from.
This n is an array, is a vector, is n of the state st.
Okay. Okay. So that was that answer to both questions.
Okay. And okay, so temporal difference prediction. Brace yourself, because we are entering the real world of reinforcement learning. I mean, this is the most famous and first reinforcement learning algorithm. Strange, because Monte Carlo methods are very natural, but this was invented by Rick Sutton, I guess, in '88. And it works this way. It's exactly just like the previous lecture. Remember, in the previous lecture, I was using the probabilities, these probabilities that I don't have anymore. And I was doing one step forward. After that, I land in the state B or A, and I use the estimate of the state B or A where I landed. Okay. Now, assume you want to estimate the value. You want the value of A. You want your estimate. And this is a recursive method. So assume you already have an estimate for A. You already have means that, let's say we have a V0 for the state A, and we want to compute V1 for the state A. Okay. What do we do? Well, in Monte Carlo methods, we would do an episode, and we would update the value of the state accordingly. The only thing changing now is that we don't do an episode, but just one step. So take your policy, and let's say the policy is choosing 1. Ask the environment what happens. Let's say the environment sends you in B. Well, you say, okay, I received a reward of +3. You see, I don't count the probability because I don't know that this reward is only 20% likely going to happen. Okay, I just write down +3. And I say, okay, I landed in the state B. So other than +3, the rest of my return is my estimate of the state B. Let's say you have the estimate, of course, of every state at time 0. And the only estimate you have up to this moment is the first estimate, V0. And of course, since some time is passed, a time step is passed, you multiply for the discount factor. And then you say, okay, not equal for the moment. Then you say, okay, this is my new estimate. This is my, in the language I was showing you before, how would you call this quantity? Your new estimate, the new value, not the new estimate, sorry, the new value that is giving you information for changing the value of your estimate.
Target.
The
Target.
Yes, the target. Thank you very much. So you're forming a new target, okay? And this is called, since this method is called temporal difference, this is called temporal difference target. And then the new estimate, how much it is? Tell me.
V0 of A.
Perfect.
And a coefficient.
Learning rate, alpha, of the target minus
the V0 of A.
Okay, is that clear? I mean, I think it's very, very, very intuitive, very easy to get this concept. Do you agree that it is exactly the same we did before? In Monte Carlo, we had just the Monte Carlo target. Okay, apart from that, everything is the same. Okay, welcome to the world of temporal difference prediction. So the temporal difference methods is just this update rule, this one. Okay. And according to what I was telling you during the Monte Carlo update rule, the learning rate has the same function, just controls how quickly you are forgetting old updates. Because when I will update my table of values for the time 100, the first update that I made in the beginning will have a coefficient of alpha to the power of 100, a dominant coefficient of this kind, and so will almost disappear. Of course, you're probably already guessing that the learning rate alpha is usually in 0, 1. Well, sometimes you can take also equal to 1, but usually smaller than 1. Okay. And this means that with temporal difference methods, we can deal with non-stationary tasks. That means a task where the probability of the environment is changing. Because if the probability of the environment is changing, you don't want to use a lot of the information you have from the past. This is very natural, I would say. And so you're just using this constant alpha to forget the past. And this is the terminology. This is a bootstrapping method, means that update the estimates, not with the actual return, but with other estimates. Does not wait until the end of the episode. I told you this is a good thing usually, and it is called, when this happens, the algorithm is called an online algorithm. The algorithm is biased, and I ask you to prove this in the exercise at the end of the lecture. But anyway, the idea why this is biased is because of the initial guess of the values. Remember that here, you see, I have to guess the initial value of the states. This initial value, of course, is the initial vector of the iterative dynamic programming technique we have seen last time. Okay, this is the point we are looking for is a fixed point for a contraction, the Bellman operator. And so we are just applying iterative recursive methods coming out from the Banach-Ciopoli theorem. And this is the first guess, the initial value, okay? The initial value give you bias for the temporal difference method. But since you are doing just one step, this method have a very low variance, which usually a good thing, means that probably it will converge eventually very much earlier than the Monte Carlo methods. Okay. Code. Well, nothing to say. Exactly as before, apart from a small detail. Take care that in the initial value you give to the states, you can't help giving 0 to the terminal states. In Monte Carlo methods, you can, because in Monte Carlo methods, the initial value you use is immediately forgotten. As soon as you sample one episode from a certain state, the value of the state is no more biased. Okay, here it's very important. If you don't give 0 to the terminal states in the initialization, then the algorithm is not going to work, because 0 is the true value. And this algorithm is going backward from the terminal states in the MDP, propagating from the terminal states. And so the initial value of the terminal states must be the correct value. All the rest is exactly the same. The update rule is the same. Now we are not saying take an episode, generate an episode. We are just saying take an action and observe what happens. Just the reward and the next state. The reward and the next state. And stop if the state is terminal, and then go on from the beginning. Choose a starting state and so on. And you see that in this algorithm is important the initial distribution. Choose a starting state means in a certain way, initial distribution on starting on states. Okay. You should ask a very important question. I mean, you are a mathematician, so I invite you to ask what you're probably asking yourself in this moment.
Sorry, I have a question.
Yes.
Is there a way how to choose optimally the learning rate alpha in both this algorithm or the previous one?
Experiments, just empirical way.
Okay.
So the answer is probably no, there is not a way.
Okay.
Sorry, I have a clarification question, which may not be the question you were saying, but just to clarify the fact about the variance, here we have a small variance because we're not considering episodes also.
Because we are
not considering entire episodes, but just one action and the reward. Okay.
Exactly. So we cannot go very, very wrong. I mean, we have just the variance for this single reward, but not we are not summing the variances on the subsequent rewards.
Okay, thank you.
Okay. Other questions? Well,
sorry, one
yes.
question. Maybe it's
Yes.
not one. What if the policy is such that we always loop on the same state and never get the terminal?
Say it again. What if the policy?
The policy is so that you always loop on the same state?
The policy cannot decide that. I mean, you are in a state, let's say A. The policy is the choice between these two. Okay. If you loop on the same state, depends on what happens later. Depends on the environment.
Yes.
Okay, but we can say, okay, let's say we have a deterministic environment. That means that you know that if you do this, you don't know maybe, but it can happen. When you do action 1, you land in B, and when you do action 2, you land in A. So let's say this, so you can go on with your question. And your policy is the policy giving in A always 2. So
well,
yes,
the question was, this algorithm never finish.
Okay. Why you want this algorithm to finish?
Okay. Well, yes.
No. Okay. Right. Okay. I see. I mean, the algorithm doesn't finish, not the one step. Okay. So this algorithm doesn't finish, of course.
Yes, it's the inner loop that doesn't finish. Never.
Yes. Okay. And okay, these pseudocodes are usually not really correct from this point of view. Of course, if there is this possibility, meaning that your MDP is not episodic or something like this, then you should be concerned about this. Take care that you will have probably a certain stopping condition here that could be, in this case, stop when I made 1000 iteration, for instance. After that, you will improve the policy. So in this case, the policy will almost certainly try also action 1. Okay, and so this will not happen anymore.
Okay. Thank you.
Okay. But in this case, you're saying something more happens. Not only the algorithm does not terminate, but state B is never visited. And so I will ask the question that you should ask. Is this method working? I mean, doesn't this question came to your mind? I mean, I started with the Monte Carlo method. I told you, okay, here there is the law of large numbers, so it works, okay? After that, I said, okay, we change the empirical mean with a constant alpha, with a running mean. Just in that case, you don't know anymore if it is working or not. And what about this? Come on, I'm estimating values according to guess I made one step before. I mean, it is very, very strange that such a thing can work. But yes, of course, it works, but under conditions that I'm not telling you now. But I will tell you in next slides. But I mean, the fact that this works under certain conditions, and depending on what condition you are using, you have different theorems. Okay, and the fact that this work really was proved in '94, and the proof is a probability proof that this converges almost surely with probability 1 to the value function, but only if this learning rate is decreasing. And if you have some knowledge of stochastic approximation theory, you should guess this. Also, for the gradient method to converge, you need something like this. And I will add more: decreasing fast, but not too fast. I will be more precise on this condition later. Okay, but I mean, it's not trivial that something like this converge. There are several details missing, but I want to give you the idea. Okay, now you have temporal difference methods and Monte Carlo methods, and this is a picture telling you which one is better. Okay, now a big question, a big open question in reinforcement learning is whether TD is better than MC or vice versa. Is Monte Carlo better than temporal difference? This is an open question, meaning you don't have a definite answer for this problem, but this is an instance of the problem, a very simple Markov reward process, where it can be shown by empirical experiments that the temporal difference methods are always better than Monte Carlo methods. I will not go into detail of this part and of the problem. I will just comment this part, that is the graph. And this is a measure of accuracy of forecasting the true values. And this is how much the loss, I mean, how much the accuracy is improving on forecasting the true value of the states according to episodes or steps for temporal difference methods. And you can see that regarding question of before, there are several learning rate, and you can say from this experiment that this learning rate is the best. Okay, but you can see that whatever learning rate you choose, and whatever, I mean, with respect to these 4 choices of learning rates for Monte Carlo methods, and with respect to these 3 choices of learning rates for temporal difference, the temporal difference method is always doing better than the Monte Carlo method. Okay, this is the gambler's ruin problem, if you know this kind of problem. You have a certain amount of money, let's say this. So you start, let's say you have 2 euros, you throw a coin, and according to head or tails, you win or lose 1 euro. And if you reach 6, you win. If you reach 0, you are ruined, you lose the game. Okay. The coin is fair in this problem, and these are the representation of the estimates of the different methods. But I think I will go. Yes. Yes.
I have a question about the plot on the lower right side.
Okay.
What about about specifically about the horizontal axis? Is it right that we are comparing in this way the two algorithms? I mean, the temporal difference is running just one action ahead, while
Yes.
instead Monte Carlo is looking at an entire episode that is composed by a sequence of actions until the terminal.
Yes.
So at each episode, in reality, is getting more information about the environment.
No, I think this number, I mean, for the blue lines, 25 means 25 steps for a certain state. And
okay, for each state.
Yes, and,
okay.
For the red lines, 25 means 25 episodes. Yes, wouldn't be fair otherwise. You're right.
Okay. But well, in reality, if you do that, is even bigger the difference between temporal difference and Monte Carlo.
Yes, yes, of course.
May I ask? So by looking at this plot, I was noticing like the root mean square error, which tends to actually go higher for the blue curves, right? The as alpha 0.15 and 0.1. If you have an intuition, any explanation of this, the fact that it's not decreasing.
Say it again.
So if I look at the TD root mean square error, so the for 0.15 and 0.1, alpha 0.15 and 0.1,
yes,
after about 25 or 50, whatever, it kind of tends to slightly go up rather than down. So I add watts, and rather than going down, it's slightly going up.
Yes, remember that the temporal difference method. Okay, I didn't tell you, but it converges if alpha is decreasing to 0. Remember? Yes, I was saying just a few words here. In order to work for this method, and working means converging to the true value function, you need alpha disappearing.
Okay, and so if alpha is really constant as it is here,
then alpha is constant, yes. When alpha is constant, you just reach a certain degree of accuracy, and then you start worsening the performance, the error of your method.
Okay, and the same happens also with the Monte Carlo, even if we don't see it there yet.
With the Monte Carlo, with a constant alpha Monte Carlo, yes, it happens again.
Yeah. Okay, perfect. Yeah. Thank you. Thanks.
Because you are forgetting the last episode, so you are not using them anymore. You are always doing an average of a finite sample. Okay. Okay.
Sorry, can I make a last question?
Yes.
And I was guessing that increasing the number of states decrease the accuracy of the estimates of both methods. But is it a bigger problem for the Monte Carlo or for the second one?
Say it again, increasing the number of states?
Lowers the accuracy of the estimate, or can be a problem for the estimate because
increasing the number of states or increasing the number of steps?
Of states, because I mean, for example, you showed us the graph that you use sometimes with 2 states. In that case, I think that it's not complicated to reach the correct distribution in a few steps. But if you increase the number of states instead of A, B, you have many states.
Well, in this example, we have 7 states, not so many.
But does this cause a problem to the accuracy of the estimate?
Well, I guess if you have more states, you need more episodes and more steps, of course. But if you take only 100 episodes and you have 1 million states, yes, of course, this completely spoiled the accuracy, but increasing you are asking if increasing the dimension of the problem force you to increase the number of samples.
Yeah, or
Yes.
if it is a bigger problem for the Monte Carlo or for the other one.
Oh, I see. Well, I never thought about that. I would say instinctively, I would say same problem for both methods. I wouldn't say the one is suffering from the increasing dimension of the state space more than the other.
Okay.
Okay, was that the question?
Yeah. Thank you.
Okay, thank you. Yes, I never thought about that. Okay, now we have a new section, but I think I will skip this also because I have given this section for you in the last part, in the exercise part. I mean, I'm not skipping it really, but I will not do it in details. I'm just trying to explain the problem. I told you that there is this open problem if whether temporal difference is or isn't better than Monte Carlo. Okay, well, I told you this is an open problem for the usual setting, that is the setting where you use infinite experience for making the estimates. In general, both methods require that you have an infinite amount of experience. Okay, but sometimes can happen that the experience is finite, the experience is costly, the experience is hard to get. Maybe the experience is some drug you are experimenting, and you don't have so many patients you can give the medicine to, and so on, or other case. So assume now that you only have a finite amount of experience. Okay, a finite amount of episodes already done. That means you can't apply your policy to do these episodes. Okay, you just have these episodes and you know what happened in a certain situations. Well, in this case, it's very natural. Compute targets and errors as usual, but do not update the value function at every episode, at every step. Just go through all the episodes, all the available experience. I don't want to call them episodes because I'm talking about experience. That means episodes for Monte Carlo and steps for temporal difference. And at the end, when you have seen all the experience, use the sum of all the errors. Okay, update in batch, update just in one step. Doesn't matter you're not getting the precise formula we are using. Okay, just get the point that you have a finite amount of experience and we want to use that. And then iterate. When you do this, this is called batch updating. Well, when alpha is small enough, constant but small enough, both these methods converge, but they do converge to a different answer usually. So, of course, none of these different answers will be the correct answer. This is impossible. You understand why? I have only a finite amount of experience. I can't say the true answer to the problem. But nevertheless, I will try to convince you that in this setting, temporal difference methods, the answer given by temporal difference method is better than the answer given by the Monte Carlo method. And I will test this with an example. Assume this. I have this experience. These are 8 episodes. Very, very easy episodes. You can see the last 7 episodes are just one step. They terminated as soon as they started. The first episode lasted 2 steps. Okay, and the question is, what are the values of A and B? the estimate of the value of A and the value of B. Say the estimate, and of course the estimate according to temporal difference and the estimate according to Monte Carlo. Think about it, because I'm going to ask you. So try to guess the value. I don't want necessarily the answer given by temporal difference of Monte Carlo method. If you are given this data and I ask you to tell me the value of the state A and the value of the state B, what would you answer? Is the problem clear?
So maybe 0 for A, but much higher for B, a little bit lower than 1 or
So
something.
why you say 0 for A?
The only experience that I have, it's very limited. I think it's just 1, and I got 0.
Okay, perfect. Good answer. And what about B? Well, in the same way, you can count the experience from B.
So yeah, for B, much closer to 1, a little bit lower maybe, or...
Well, you can count it.
Oh, yeah. So like...
I would say 7/8, right?
Yeah, 3/4, yeah, exactly, yeah.
Okay, perfect. I would say you are a Monte Carlo guy. And what about other answers? Is anybody there that has a different answer?
Well, one other way to see this problem is that when we are calculating the value for A and we see that we go to B, do not use just the information and then we add the 0 from B, but the estimate of 3/4 of B also for A. I mean, we had a transition from A to B, and B have some values that is not 0.
So let me recap if I get correctly. You are saying, okay, from A, I'm looking one step, okay, I get 0 as reward, but then I land in B, and so I will estimate this according to the value of B.
Yeah,
okay,
and not using just 0, but the whole set of B.
Yes, and now I have to compute the value of B. Well, B is the same for, I mean, every time I get in B, then I terminate. So we agree that the value in B is 3/4. I mean, nobody would say different.
Yeah.
Okay. And so you are saying that the value of A is the reward I obtain 0 plus the value of B, which is 3/4. So you are saying that you think it is correct to bootstrap the value of A with the estimate of the value of B.
Yeah.
And so you are a temporal difference guy. Okay, this is the temporal difference answer, and this is the Monte Carlo answer. Okay. At least, I mean, you should have the intuition about this. But I told you something. I told you in the beginning that I would try to convince you that this answer is better than this. And this is why. Well, this is a theorem. I'm just telling you, but in the exercise at the end, I ask you to prove this theorem, that the fact that the TD answer is the correct value, not correct, I mean the true value is the true value, assuming in order to have a true value, I need a model. So is the true value assuming the maximum likelihood model. What does this mean? When I have experience, I have a notion of maximum likelihood probabilities. I mean, what is the model? What are the probabilities underlying a certain Markov decision process that I don't know, but that contains the states A and B and gives, at least in this situation, these rewards? And when in B, always terminate. What are the probabilities of such a Markov decision process that would give me this experience with the maximum probability? I mean, if you consider this question and you build this model here, if you put this number as parameter, let's say P1 and P2, then and you find the value of the states according to these two parameters, then you will find that the temporal difference answer, that is this one, is the value given by the parameters that maximize the probability of the previous experience to happen. I'm not sure I was clear. Okay, this is the maximum likelihood concept. If you don't know it, then probably you have some difficulty in getting this this concept. But the fact is that the answer of temporal difference is building a model inside, and is building a model which is very likely the true model, having seen only this experience. And after that, temporal difference will compute the true value. So in this sense, the temporal difference answer is the true answer, given just that experience that we have. Okay. Please give me a feedback.
Sorry, I don't get why TD is always better, because I was thinking about the example that you now draw. But what if A never goes to B and it just terminates with reward 0? Then Monte Carlo is better, but maybe there is something that I didn't understand. No, because in this case, we all, I mean, the answer that we gave you was based also on the example that you were explaining us before, the leading graph, let's say, that you showed us, where we know that from A we could have gone to B. But what if this possibility, I mean, is not true? So from A we cannot go to B.
If I tell you, if before asking you what is the value of the states, I'm telling you that the model is this one. And then I ask you what are the value of the states. You would answer this, right?
Yes, okay.
Okay, so in this sense, when I tell you that the value given by the temporal difference method are the value given according to this model, well, you can say, okay, but these probabilities, you just invented them. So why they are the true probabilities? Well, I'm not inventing them. These are the maximum likelihood probabilities of the model. Maximum likelihood with respect to what? With respect to this experience, which is the only data we have. Okay. In some sense, think about this. I'm asking you to give me the expected value of tossing a coin. What's your answer?
Well, 50% heads, 50% tail.
Of course. And now I toss the coin 10 times. And 9 times out of 10, it comes tails. And I ask you again. You can give me two answers. You can still assume that the coin is fair, and then the answer will be independent of the experience. But I mean, 9 out of 10, maybe you have some suspect. And once you have some reason to think that the coin is not fair, what is the best answer you can give me?
I mean, 9 out of 10. I don't remember if it was I thought but yeah.
Okay. So this is the point. By this experience, you are evaluating the probabilities of the coin. And now you say the probabilities of the coin are this one. And then you give me the answer. In this sense, this answer is better. But of course, Monte Carlo answer is completely plausible. You can give that answer, but
okay.
In some sense, at least in this case, there is a reason to make the statement that temporal difference is better.
For example, then I quit because I don't want to waste your time. If you imagine that from A it starts an arrow that goes to the square with 100% probability and r equal to 0, then Monte Carlo and temporal difference are equal.
Yes. So you let me.
They should give the same result in this case.
So you mean if we have also an arrow this way?
Yeah, and not the arrow that there is in your picture, for example.
So not this one?
Exactly.
Okay, but if I don't have this arrow, then this experience cannot happen because from A I go to B, right?
Okay, yeah, that's true.
So this is okay. This is a different model that would give different probability, different values. But if you are telling me, no, I think this is the true answer, I will have an easy life telling you you are wrong because this model is not compatible with what happened.
Okay, perfect. Thank you.
Okay. Well done. So remember this. We have now some qualitative argument to think about Monte Carlo and temporal difference properties. What we are saying is in a more probabilistic language that temporal difference method they exploit the property, the Markovian property of the environment, because they build the model for the Markov decision process, and then they use the lecture 1 2 days ago that was very, very deeply using the Markov property. They use that lecture to compute the value. And Monte Carlo, on the other way, it just ignores completely the Markovian property of the model, because when I do an episode, I just don't care, Markovian or not Markovian. I'm just evaluating the value of this state, just going up to the end, the true end, and I will see the true outcome. Okay, so I don't care if the environment is Markov or not, because I'm just doing the true experience, and I'm computing the true value, a true sample of an unbiased sample of the value I want to estimate. So this means, as a consequence, the temporal difference is more efficient when the environment is Markov. On the other side, this means that Monte Carlo is more efficient when the environment is non-Markov. Non-Markov happens much more often than you can think, because every time you have something that you cannot fully observe, you are putting yourself in a non-Markov state. Maybe the underlying environment is Markov, but if you can't get every feature of the underlying states, only a partial observation of the state, then you end in a non-Markov observation. I don't know if this is clear, but just get the intuition. Okay. Now, let me check if you have an idea. Let's go back here. I'm asking you to invent a new method. Up to now, we have one method called Monte Carlo that starts from state A, goes all through one episode until the end, and then does something. And then we have another method called temporal difference one step that starts from A, does one step, and stops, and makes these things. Can you guess another method? Can you invent another method? In some sense, in between the two.
One that does 2 steps or 3 steps and then guesses. Some steps and then guesses.
Very, very good. Thank you very much. In this sense, do you agree that Monte Carlo methods are methods with infinite steps? Not really infinite, of course, but meaning I do as much as I can. In between, I have methods which are called n-step temporal difference methods. And they do, of course, n steps. So a two-step method would do first step, second step, and then I stop and I bootstrap with the value of the last state, in this case, state B. You understand the terminology bootstrap with B right now, meaning I use the estimate I have for the state B from before. Okay, these methods are called n-step methods. And if you are asking, and you should, which n is better, as usual, there is not a definite answer. It depends on the problem. This is the application of n-step methods to the problem of before, the random walk. And in this case, you can see that the best n is n equal to 4. Corresponding to a certain alpha, of course. If you change alpha, then you have other best methods. You see, this is the way to get the best parameter. Usually, when you're facing a problem, you create a toy version of that problem, and you use the toy version to do something like this. And from that toy version, you decide, okay, I will use 4 steps with a learning rate of 0.4, because on the toy version of the problem, these are the parameters. This is called hyperparameters tuning. Okay, and then you go to the real problem. Of course, if you are asking yourself this, you have no theoretical guarantees that what happens in the toy problem will happen also in the bigger problem. Sometimes you have to rescale these numbers in function of how much you are changing the dimension of the problem. Okay. And last thing, I told you that sometimes n equal to 1 is better than n equal to 2, but sometimes 2 is better, sometimes 4 is better, 5, 6, sometimes 8 is better, and so on. What if you want to use all of these methods all together? Can you invent a new method? Not sure the question is clear. I don't want the compromise of choosing a single step. I want a method getting all the n-step methods all together in only one method. Remember what is this that I just wrote? This is the TD target, right? Can you tell me the two-step TD target? Please. The first reward. The second.
Plus gamma
Yes.
R equals 2, etc.
Plus gamma square, the value of the st plus 2. Okay, so you have several targets. Let's call the first one target T1, the second one target T2, and so on. We have all these targets. Well, I can use as a target every combination, weighted combination of these targets, as soon as the weight sums to 1. I mean, I could use, if I trust T2 and T3, I could use this as a new target. You see that the language of the target, how powerful it is. It allows you to create new methods. Now, if this method works, this is another question. Okay, you need a theorem. You need to invent this theorem, experiment it if it is working. When the empirical evidence is showing you that this method is working in difficult problems, maybe better than other methods, then you start looking for a proof of why this method is working. And this is a complete different part of the story, okay? But anyway, we are not interested in this one. The best method you can use in this sense is a method weighting the return Tn by a new parameter to the power of n. N minus 1, I think. So that the first one is weighted, is not weighted. And in this way, the target you are using is the sum for n going from 1 to infinite. And this is called TD lambda target. And of course, we need to divide by this. No, multiply. I mean, the sum must be 1. So I guess I have to multiply times 1 minus lambda, right? Okay, this method is called TD lambda. We're not doing this in this course, but it is one of the most advanced methods in reinforcement learning. And in this sense, one step, if you think about this, is equal to TD with lambda equal to 0. So it is called TD 0 usually. And Monte Carlo is temporal difference with lambda equal to 1. And it's called TD1. Okay. Questions? Because we are into a new part, which is the control part. Maybe I'm losing you. So remember, we were doing prediction, and we have found two different families of methods. Monte Carlo methods, looking up to the end of the experience, and temporal difference methods, doing just one step of experience. And now I just told you that you can also extend them and doing 2 steps, 3 steps, or just using all the steps you can do. But anyway, we were doing prediction. Now we have to do control. That means improvement and cycle with prediction. Okay. Maybe 5 minutes of pause, because I'm scared that I'm losing you. Let's get back at 16 at 4. Luigi,
Okay.
what do you think?
Yeah, perfect. See you in 5 minutes.
Okay. Okay, so let's start with the control cycle. This is a very classical picture in this in reinforcement learning. I guess it comes from David Silver's slides from 2015. I'm not sure, but everybody is using this, so I'm showing this to you so you can understand what this means. And this is a new picture, right? I haven't shown you in the first lecture. It's the first time you're seeing this, right?
You showed us the one with V, I think, rather than.
Okay. So you already know what this means. Very good, very good. So this is with Q. Why it is with Q? Because remember, we are in the model-free case, and up to now we were saying, okay, with this method, Monte Carlo or temporal difference, we are estimating the value function. Okay, we are estimating the value of a state S, the value of every state S. But now we have to make the improvement. Remember how the improvement works? I am in a state, let's go again to this part. Here. Let's do this way. Okay. Remember how the improvement works. I am in the state A, and usually my policy chooses between 1 and 2 in different proportions. But now I know the value of every state, okay, because I computed, I evaluated, I terminated the prediction phase with some methods. And now I want to evaluate the best action. What do? I say, okay, if I choose the action 1 from here, what happens? Well, it can happen this, and then I will have 10 times 0.8. So in this direction, I will have 8 plus the value of A. Forgive me if I don't put the discount factor, okay, just for the sake of exposition. And if I go in this direction, I will have 0.6 plus the value of B. Let's say that the value of A is 1, so this is 9. Let's say that the value of B is 10, so this is 10.6. Okay, sorry. Sorry, I'm a bit tired. So let's say I go in this direction. I will have 8 as the reward, and then I will have 0.8 times the value of A. And in this direction, I will have 0.6 times 0.2 the value of B. And so I will have a total value of this action. All this number that I formed here, the sum of them, is the value of the action 1 from the state A. Remember this, right? The Q value, the quality value of an action. Now, if I know the value of the states, and I can do the same in this direction, so I can check the value of the action 2 from the states A. Let's say that this number is 10 and this number is 11. The action that I will choose is, of course, the action 2, because the value of the action 2 is bigger than the value of the action 1. Okay? But to compute these values, what do you need? In this computation, you see, I have the model. I have the probabilities of the environment. So what I'm saying is that the value of the states is useless in model-free case to compute the Q value of the action. And thus, you cannot use this to make the greedy policy improvement, to choose the best action, right? Is this clear? So we need the value of the actions, not the value of the states. Okay, so now you're going to kill me because you say, okay, we spent 2 hours learning how to evaluate the value of states, and now you're telling us that this is useless. Yes, but I'm also telling you that all the things we have said for the state S holds in the exact same way without any modification for the Q value. Simply, when you do an episode for the Monte Carlo methods, instead of estimating the value of A, you want to estimate the value of A and action 1, you just start from here. The episode will not start from A, choosing a random action between the two. The episode will start from here, meaning that the first action is fixed. And then you will have an episode, you will take your final return, and then you will compute the empirical mean and so on. Everything is in the same exact way, okay? So the prediction part works exactly the same, but remember that from now on, the prediction part is about the Q value. We're not going to use the state value anymore for a long time now. Okay? And then we are asking ourselves, is the next step in the policy iteration framework that we were following 2 days ago, if the policy improvement, the greedy policy improvement is working. So this is the big question. Can you try to tell me if, in your opinion, doing a greedy policy improvement in this model-free setup works? I mean, gives an algorithm, a method that works, means that gives you an approximation of the optimal policy. Remember, you start from a policy, P0, Pi0. This is the initial policy, let's say the random policy. You evaluate this policy, you obtain the value, and I told you this is the Q value, okay? And now you use this value to produce a new policy. Remember, the new policy is the policy choosing the max value of actions for every state. This policy is called the greedy policy with respect to the Q value. The greedy policy has a very particular property, that is, when you think about the greedy policy, something should pop out in your mind immediately.
It's deterministic.
Deterministic, thank you very much. The greedy policy is deterministic. Remember, in model-free case, deterministic is bad. Why? Because all the methods we are looking at In particular, Monte Carlo, it is apparent, but also temporal different methods. Maybe I haven't said it explicitly, but they rely on the fact that every node we are interested in the evaluation phase is visited infinite times. I was telling you the Monte Carlo method works because of the law of large numbers. Okay, we need a limit for the law of large numbers. So the number of visits to a certain state must be infinite. Okay, now here the nodes we are concerned with are the action nodes. That means every pair state action, this is the node that we have to visit infinite times. Now imagine that your policy, the greedy policy here, is choosing in this case, is choosing always this action. This is the greedy action. Then it means that in this evaluation phase, you will never visit this node. You will never visit this action. And so the method cannot work, because you are saying, okay, this is the best action I can do, but you don't know anything about the other action. So it's very unlikely that what you're saying is true, is giving you the true value. Okay, so in general, when you are in the model-free case, you can't be deterministic. On the other side, on the other way, remember that the optimal policy is deterministic. So once you know that the best action is this one, then you are correct. You can say, okay, I will look only at this action. But until you know this, you can't help visiting all the action from every state. This can you get a concern, a tension between the need of exploration, visiting all actions, so you want to explore every action, and the need of using the action that are better. When you choose the greedy action, it's not because you like this action or I mean, it's because you like this action. It's because this action is the best action you can see up to this moment. Okay, so this is called exploitation. So there is a tension between exploration and exploitation in this kind of problems that is apparent in this example. This is what is called the multi-armed bandit problem. This is a three-armed bandit, meaning a slot machine with 3 arms, or if you prefer, 3 different slot machines with 1 single arm each. And imagine that you have an experience consisting in 2 episodes. Here, one episode is just 1 step, 1 play. You played 2 times on each machine, so you have 6 episodes actually, and you obtained this reward for the left arm. You obtain this reward for the center arm, and you obtain this reward for the right arm. I'm now asking you to choose the next arm. And of course, you want to maximize your chance of winning. Try answering. Which arm would you choose next? Left, center, right.
Well, maybe just looking at the data that we have and not considering, I mean, the slot machine as they are slot machine. The average reward for the center one is the highest. So the next one maybe will be the center one.
So you see here the average reward is 7. Here the average reward is 6. And here the average reward is 0. Okay, I mean, with this limited data, you would choose the center one. Okay, assume now you get 0. What is your next choice?
Well, I update the average reward, and now is well, is 14 divided by 3 for the center,
which is less than 6, right?
Yeah, and so I will move to the right one.
Perfect. Right. And you go on this way. Now, next question. Do you have any chance with this method of going back to use the left arm?
No, because whatever I get, the average reward for the center and the right will be always greater than 0.
Greater than 0. So we are saying that it is very natural in this situation with this limited data, playing always center and right. But this has a strange consequences. I mean, we are saying that with just 2 plays on the left arm, we can assume that the left slot machine is bad. It's not the best one. I mean, come on, maybe we were just unlucky. I would give it at least 10 other shots to the left machine, right? Depending on my resources, of course. This game is costly, probably. I'm spending €1 per play. So it depends on how much money do I have. It depends on constraints. But I mean, it's not so clear. What you were choosing was the greedy action, okay? You were always choosing the best action up to that moment. But you see, there is this need, this apparent need of sometimes choosing an arm which is not the best one. Okay? And this is what is called tension between exploration, exploitation. Okay. And so your algorithm is not really the best one. Can you modify it? And could you try to guess another algorithm that sometimes comes back to the left arm?
Well, instead of having a probability distribution that is 1 on the biggest, we can start with a uniform one, and then adjust it. I mean, proportionally to the average reward.
Oh, this is it's not the first time that this answer comes up. Must be very, very natural. Okay, this would be a way. So okay, in the beginning we start with uniform. So you mean we do I don't know 10 plays per each, more or less, or we draw from a uniform distribution 30 times, which is more or less the same. And after that, we start weighting the arms, the probability of choosing one arm with the reward we are getting. Okay, this is what you're saying.
Yes, this is the idea, yeah.
Okay, so I mean, we are assuming that I mean, we are starting this when we obtain a positive reward on every machine. Otherwise, we are waiting with 0 and it is not working. Okay, this can be a way, but there is another way, which is I don't know if it is simpler, but it is proved to be one of the best, and it is also one of the simplest, and it's this one. We choose the actions not in a greedy way, but in a greedy way 90% of the times. The other 10% of the times we choose completely random. you see, we are not waiting with a reward, but more or less it's similar to your idea, I would say. We introduce a random choice sometimes in formulas. What I'm saying is I choose an epsilon, again, a new parameter for our problem. Let's say epsilon equal to 10%, 0.1. And then I'm choosing one action in a state S with probability 0.9. I'm choosing argmax of the Q values. And with probability 0.1 uniform on the others. Okay, so if I have 100 actions available, then at 90% I will choose the best one. And each one of the 99 remaining, I will choose each of them with 0.1 over 99 uniformly. Is this clear how this works? I mean, like the formula seems more complicated than it is really. This, you must get this. So I'm staying on the slide for a few seconds because the epsilon greedy policy improvement is the one we are using forever now until the last lecture. Okay, so from this moment on, we are no more taking a greedy improvement because otherwise we are not exploring every action infinite times. We need to introduce a random choice. At every timestamp, there must be a chance, as small as it can be, but there must be a positive probability for choosing every action. And this is the best way to obtain this.
Is this a trick for escaping of local minima?
Well, this will be, of course, the exploration part is the part that will keep you moving from the local minima when we will do approximation, yes. But remember that in the tabular finite case, we are assuming finite MDP, there is the policy improvement theorem. So we are always improving and we are reaching the optimal policy. In the tabular case, there are no local minima in some sense, because there is this theorem, the policy improvement theorem, that the policy is always improving and the improvement is stopping only when we reach the optimal policy. Remember this theorem,
yes,
right?
But if I reach the maximum, why should I move from it?
If I reach the maximum, okay.
Why should I move from this choice?
Say it again. I'm not sure.
Why should I move? Why should I change my choice?
Okay, what do you mean when your control cycle is converging to the optimal policy?
Yes, why I should change my mind if I have
you will not change, because I will tell later, this algorithm, the family of control algorithms coming from this epsilon greedy policy improvement step works when epsilon is actually depending on the time and is going to 0. Okay, so when you are converging to the optimal policy, the exploration part probability is going to 0. So you are becoming greedy at the end. So you are not changing your action.
Okay, okay. I understood.
Okay, if not, we are chatting around, it's called this situation. We reach a maximum, and then sometimes with probability 10% in this case, we go away from this maximum. But then, since we are choosing the greedy action 90% of the times, we will get back to this global maximum very, very soon. And we are chattering around means that we are moving from this maximum area.
So in practice, it's like a gradient descent, a sort of gradient descent.
Yes, this part of the exploration. The idea is the same. Yes, in the gradient descent, if you don't make the learning rate converging to 0, you have a similar problem, right?
Yes.
Okay.
One question about this. So in the otherwise branch of this function,
Yes.
you put all the other states, okay?
Action.
And sorry, all the other action. Even if I mean, okay, the maximum is in the upper branch. In the lower branch, the otherwise one, you have all the others, regardless the difference of value between them, right? I mean,
yes,
it would be
yes,
that the second, the most available one is together. It has the same probability to be drawn.
Yes,
than the
with
worst
this
ever.
scheduling, yes. Of course, okay. You can do also what you are suggesting. That is weighting the action by their values.
Okay.
This is possible also, yes. Okay, this was the question.
Yes, thank you.
Okay, so this kind of policies, epsilon greedy policies, enter a family of policies which are probability distributions, which are called soft. Soft means everywhere positive. Okay, you don't have state action pairs with 0 probability of happening. Epsilon soft means a little bit better, means not only positive, but uniformly bounded from below positive in this sense. Okay, and between the soft policy needed for exploration, so soft policies are needed for exploration. Otherwise, something you're not going to explore. The 0 probability pairs, you're never going to explore them. You are not going to explore them infinite times. And between them, the epsilon soft are the most greedy, most, let's say, closest to the greedy ones. So it makes sense to look for your policy, optimal policy, which you know to be a greedy policy, which you know to be a deterministic policy, essentially deterministic policy. It makes sense to look for that in the family of epsilon soft policies. And we have a very, very good news. We have a policy improvement theorem also for the epsilon soft policy that states that the epsilon greedy policy is an improvement between the epsilon soft policies. Remember, this policy improvement theorem is very, very important in convergence proofs for the tabular case. And this is exactly this that we will miss in the next week in the approximation part. Okay, and let's go on. So this is just a quick slide to tell you that then we are settled. Now we know how to do the control cycle. That is, we know how to do the policy evaluation. We know several methods for doing the policy evaluation, that is with Monte Carlo or temporal different methods. We know that we need to evaluate not the state value, but the Q value function. We know that the policy improvement can be done if we accept the compromise of choosing the policy not greedy as the greedy improvement, but choosing the new policy as epsilon greedy improvement. Okay, so we have a control cycle. Remember, the name of the original control cycle was policy iteration. That was the control cycle done with the policy evaluation made exactly as I told you in the last lecture, and the policy improvement exactly as I told you in the last lecture, that is the greedy improvement. In that case, we talk about policy iteration. I told you in the future, that is now, we will do the policy evaluation and the policy improvement in different ways. In this case, we say that we are doing general policy iteration. Okay, and the label is GPI, this one. It is something that you find very often. So now the question you should ask is the same as before. Okay, this general framework, does it work? I mean, if we do this, we are converging to the optimal policy? Well, the answer to this question is very easy. Of course, no. The optimal policy is greedy. We are converging with the epsilon greedy policy improvement. We are converging to an epsilon greedy policy. So cannot be the optimal policy, okay? So let's have a look if we have some general results that can clarify under which condition we can converge to the optimal policy. Well, it's very, very natural. There are two conditions that must be satisfied. If these two conditions are satisfied, I will explain in a moment what these conditions are for, but they are very natural. If these two conditions are satisfied by the algorithm, by the method, you see, I'm talking about the Monte Carlo method, the temporal difference method, but they are actually family of methods. Monte Carlo methods, plural, means all the methods that estimate the expected value that you are looking for with full episodes. The temporal difference methods are the one that estimates this value with partial episodes. In the extreme case, with just one step of episode. Okay, and the way you put all together in an algorithm, this makes part of the method you are looking for. Okay, so we have several methods, and now we have a theorem stating that if the method is Monte Carlo and satisfies these two hypotheses, which are called, the first is the hypothesis for the policy to be greedy in the limit, GL, and the second is for the policy giving you infinite exploration, IE, and altogether GLIE. If the method is Monte Carlo in the Monte Carlo family, and the policies included in this method, the policies that makes part of the improvement part, then all the policies you are using are satisfying these two hypotheses, then the method converges to the optimal policy. And these two hypotheses are very, 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 very natural. Greedy in the limit. Come on, the optimal policy is greedy. And if you are not greedy in the limit, if your family of policies that you are using for the improvement step doesn't converge toward a greedy policy, you can't get the greedy optimal policy, of course. This is compulsory, I mean. Okay, so greedy in the limit means that the policy converges to a greedy policy. That means that this one, the probability converges to, the policy converges to a deterministic policy in the end. And remark, in the case of epsilon greedy improvement, this one, this is satisfied if the exploration part converges to 0. You agree on that, right? If this is converging to 0, then the policy is converging, is accumulating all the probability on the argmax action. And the other condition is required by the law of large numbers, that all state action pairs are visited infinitely many times. And the epsilon greedy exploration, the epsilon greedy improvement ensure this. So this means, for instance, that epsilon greedy improvement, epsilon greedy control cycle is converging to the optimal policy as soon as epsilon is not just one constant value, but is a sequence of values converging to 0. Okay, and this is what is said in this new slide. So you see, the example means that applying the previous theorem, we obtain a new algorithm that is giving the optimal policy. Okay, the algorithm is, the evaluation part is this one. This is computing the empirical mean of the returns. Remember the evaluation part. And then after one episode, we improve the policy by epsilon greedy, with epsilon going to 0 in this, with this schedule. In my last sentence, there was a mistake. I don't know if you got it. Which was the mistake? I told you in this line, I'm doing the empirical mean of the returns of the episodes. Remember, this is exactly the line we were using for the evaluation Monte Carlo part. Or you don't remember because this is a crash course and you're probably almost fried now. But trust me, this is the same line that I showed you when I told you this is the way we can compute the Q value of states. Now is pair state actions. The Q value of states by computing in an incremental way the empirical mean of episodes. But remember, at that time, the policy was just one policy, and I was doing several episodes with the same policy. Now I'm doing just one episode, and then K is increasing. So let's say I'm doing episode number 2. Now K is equal to 3, epsilon is equal to 1/3, and now I change my policy. Now the policy is no more the same as before. It's the epsilon greedy policy with respect to the estimate of the Q value up to now. So the next episode will be done with a different policy. So I'm not really evaluating the value of one single policy. And this is the meaning of this sentence. We are not doing a true mean because the policy is changing. It's just like, imagine I'm asking you to compute the by the law of large numbers the expected value of throwing one regular dice with 6 phases. You throw the dice once, you take note of the outcome, and you go to throw the dice a second time. I tell you, oh no, wait a moment, and I give you a dice with 8 phases. Yes, they exist. If you play Dungeons and Dragons, you know this. I give you a new dice with a different number of phases. And okay, go on. You tell me, but come on, no, I need the same dice. I cannot evaluate the value of the expected value of this dice with another dice. Okay, this is something like this we are doing. But anyway, since the algorithm satisfies the Glie hypothesis, then it works and converges to the optimal value function. Okay, now can you try to invent a new solution to the exploration problem? I mean, improving with the epsilon greedy policies works. So you have exploration, but can you guess another way to ensure exploration of all the state action pairs? Something related to the initial distribution. If you can choose the initial distribution of the states, the starting state pair of episodes, what can you do? Try. You can choose the starting distribution.
I would choose a starting distribution which is the more likely to the maximum.
Well, you can choose the initial distribution, but you don't know the solution to the problem. So you can't choose the initial distribution already optimal. This is what you were saying.
I could try to infer it. I don't know.
No, I'm just asking you a way to solve the exploration problem. The fact that we need to explore all state action pairs infinitely times. And now I'm telling you that you can choose your initial distribution of states actions, sorry, or initial distribution of the pairs state action.
You choose this positive on every pair state action.
Exactly. You choose what we call the soft policy, the soft initial distribution for the starting pairs. And in this way, whenever you start a new episode, you are choosing a random state action pair. So exploration problem solved. And this means that you don't need anymore the epsilon greedy part. You don't need this. You can just improve the policy in the old-fashioned way, greedy improvement, just with the argmax. This is an option that you have if the problem allows you to choose the starting distribution. When you do this algorithm is called Monte Carlo with exploring stars. So you choose an initial distribution this way, and this, of course, guarantees that all the state action pairs will be visited infinitely many times, and you can do greedy improvement. Okay, if you think about this, this is a greedy in the limit. Of course it is greedy in the limit. It is greedy at every step, not only in the limit, and with infinite exploration because of the exploring stars. So it converges for that theorem I was telling you before. Okay. Questions?
Yeah, so just to clarify the exploring starts approach. So basically, it means we first explore all the different possibilities, and then we use a greedy approach after we spend some time in exploring all the different states, right?
Yes, yes.
Okay.
Now, I must point out that of course, again, also this algorithm described in this way, there are several other details you should precise. I mean, this is still a family of algorithms, okay? I'm just giving you the ideas of the techniques that we have to solve the problem exploration, exploitation that I was talking about. Okay. Now, this is for the Monte Carlo methods, okay? And what about temporal difference methods? So how can we do a temporal difference control method? Remember, the temporal difference update rule is this one. Now, this one is, think about this, is the same update rule I showed you for the temporal difference method for the value of a state. The value of a state is updated by the value of the state plus this, the reward which are obtained, plus the value of the next state minus the original value of the state. Remember, this was the update rule for the value function. And now the only thing is that when I reach the next state as prime, in order to use the previous estimate, I need to have also one action, okay? So if I can choose this action with the policy I'm evaluating, and so I obtain the evaluation rule, or the evaluation part, the prediction part. And okay, this is the next slide. So for the moment, assume I'm taking this action, a prime sampled from the policy, from the state S prime. The same policy that I am evaluating, meaning that also A is taken from the same policy that I am evaluating. Now, okay, now this is the control part. Okay, if I do this, okay, this is important. If I do this, I'm just evaluating the Q value, okay? What is the control part, the control cycle associated to this update rule? Okay, not clear at all. This is the prediction part, right? Now I need to put together also the improvement part. How do you do the improvement here? I mean, this is one step of evaluation. What is the next step, the improvement step? This is, let's say, this is P0, or let's say P8. We have made the 8 steps of evaluation. So now I have the new policy P9. What is? You need to improve the previous policy.
I use the greedy policy on P8.
Yes, I can take the greedy policy with respect to Q, right?
See.
Not with respect to P8. With respect to the greedy policy is taken with respect to a value vector. Perfect. Let's say, since we know in advance that we have to explore, we will take the epsilon greedy improvement. And now we choose a new action from this new policy, right? Well, if you think about it, this means that this is equivalent in inserting here the choice of the action, the new action I'm using in this target, chosen not from the original policy, but already from this. What I'm saying is that you insert this choice directly in the update rule, you obtain the same as if you are doing the two steps in a separate way. So the Sarsa rule, the control rule given in this in this setting, in this context, in this language, is this one where A prime is chosen by the epsilon greedy policy with respect to Q. Okay, this update rule is called Sarsa control update rule. And Sarsa comes from here. That you're starting from a state action pair, you get a reward, you get the next state, and you take the next action in the epsilon greedy way. I can feel from your silence that this is not clear, so ask, please. This is a new family of methods, if you like. Maybe I can show you the next slide. Maybe here it is more clear. You see, you take action A, observe what happens, the reward and the next state, and then you choose an action from this next state. And you see, when I say choose an action, I must specify which policy you are using. If I'm evaluating one policy, then the policy is that one fixed and I don't have to specify it. But if I'm making the control part, I need to specify which policy I'm using. And in this case, I'm using the epsilon greedy policy given from Q. So A prime, this one, is from epsilon greedy. So if you think about this, this is no more the update rule for a fixed policy. As usual, I'm putting in the target the improvement. Well, this makes sense, right? Because the target must be an improved estimate of the value I'm estimating. And now the improvement doesn't mean that I want to converge to the value of a fixed policy. I want to converge to the value of the best policy. So it makes sense at every step changing the policy. As usual, the question here is, does it work? I mean, is this converging to the optimal policy? Well, it is if some conditions are satisfied. And the first condition is the same as before. That the sequence of policies must satisfy this hypothesis. And the next condition is a common condition in stochastic approximation theory. And this is the one I was telling you before, that the step sizes, the learning rate must be a sequence of learning rates, and that sequence of learning rates must be large. That means they are not converging in L1 norm, but they are not too large. That means they are in L2. And this is the condition. Spoiler, 1 over k satisfies this condition. Okay, so you see we have two different hyperparameters, the exploration rate and the learning rate. both of them, if we want to converge to the optimal action value function, which is not always the case, if we want this, then we need a schedule for both the exploration rate and the learning rate. A schedule that must be converging to 0 in some sense, very naturally, because the exploration rate must give you no exploration in the limit, because in the limit, the optimal policy is not exploring. I mean, if you know what is the best action, you don't want to explore other actions. I mean, you know the best action, do that action and nothing else, okay? But in order to find the best action, you always need to explore. And the learning rate, in the same way, when the learning rate encodes the trust you have in your new target. If the learning rate is 1, it means that you are completely replacing the old value with the new target. If the learning rate is 0, it means that you trust the old value and you are just dropping out the new target. In the between, you have intermediate values, and the learning rate going to 0 means that once you're doing more and more and more and more steps or episodes, you are trusting more and more and more your old value. I mean, if I have done 1 million episodes and my estimate is 42 for the value of the state, and now I take one episode and the outcome is 50. I mean, I don't want to change from 42 to 49 because of this 50. This 50 must count 1 over 1 million in some sense. So I'm not changing very much this estimate. Okay, so it is very natural. These conditions are very natural. Okay. Questions here? Okay, it is 5 p.m., but I would like to go on for, let's say, 15 minutes to quickly finish the lecture. If you don't mind, I mean, of course, if you want, you can go. But if I finish the lecture, at least we have a complete lecture for the recording. And also, if you go now, you can listen to it later. So I will keep talking. I would say 15 minutes should be enough. Plus questions, of course, if you want to ask, and feel free to go if you can't stay. So up to now, we have seen the control part. Now I have 2 slides. Okay, this is the code that I was showing you. We have 2 slides that I will skip. These are on the n-step methods, but I want to do the off-policy case. Oh, so recapping this part. We can do the prediction of a policy, and then we can do the control, meaning we alternate the prediction step and the improvement step. And we discover that since we have to explore, but in the same time the final policy must be greedy, we have this tension between the need for exploration and the need for choosing the greedy actions. And we solve this problem with the epsilon greedy improvement. Okay, and this is a good solution, but this solution is a compromise. It is clear why it is a compromise. In particular, if I'm not making epsilon decaying to 0, I have no chance to obtain the optimal policy. So now I will propose you a completely new framework to work out this tension, to solve this tension between exploration and exploitation. You see that in our algorithms, we do two important different things. In one situation of the algorithm, we choose the actions, from a policy. And in another situation, in the update rule, we update the estimate of value in a table, which is called Q usually. Okay, do you agree that these are two conceptual different steps? For instance, I can show you the pseudocode here. You see, here I'm choosing this action. Here I'm choosing the action A prime. Sorry, take action here. I'm choosing the action A using a policy. Okay, the fact that the policy is derived from Q it doesn't matter for the moment, but I'm choosing this using a policy. And then in this update rule, I'm updating Q. So in some sense, this is the rule for choosing the actions. This is the policy for choosing the actions. This is a table to store the values that will give you eventually the optimal policy. Correct? So what I'm saying is this: update estimate in the table, storing at the end the optimal policy. Well, since these are two different steps, guys, why are we always using the same object? I mean, why are we using Q to store the value of this policy? Why is this policy giving the value of Q? I mean, this is not, I mean, this was very natural, but this is, if you think about it, this is what is causing the problem. This is the policy needed for choosing the action. So this policy must be, tell me, what this policy, do you need it greedy or not greedy? In your opinion? The policy choosing the actions in the exploration, exploitation tension. Which side is? Say it again.
Not greedy.
Not greedy, because this is a policy that must explore. Pi must explore, right? But the table Q, I mean, this is at the end must be the optimal policy. So this is a table which is not concerned with the exploration part. This can be in some sense greedy. What I'm saying is this, is that conceptually we have two different policies in this game. And up to now, we were using the same policy. But in this family of methods called off-policy methods, we detach the two concepts and we use two different policies. One policy is called the behavior policy. And this is the policy that we are using to make the experience, to form the targets, to form the episodes. And then we use the samples from this policy to evaluate a different policy, which is the target policy. This target word is nothing to do with the target in the TD target or Monte Carlo target. Okay, this is a different policy, which is the policy which will be the table storing the values used to approximate the value of the optimal policy. In this way, you have no more this tension, because the behavior policy can be an exploratory policy, while the target policy can be a greedy policy, can be a deterministic policy. Okay, if you are, if you think a little about this, this is the difficult part. I mean, come on, if I sample experience from one policy, how can I evaluate a different policy, a different probability distribution? I mean, the same as before. I ask you to throw the dice with 6 phases to evaluate the expected value of the dice with 8 phases. Yeah, this seems impossible. Actually, there is a tool, there is a formula, a very easy formula to change the expectation just by using ratios of probabilities. I will not enter in detail. These are, how are they called? Okay, I'm sorry, I have a I don't remember the name, the word I was going to tell you, so I will not tell you. And anyway, there is a technical statistical probabilistic tool to change the experience from one probability distribution to another. So we will not enter the detail, but just to tell you that if you go on with this kind of argument, then you end up with this algorithm, which is the very famous algorithm called Q-learning. This is, I would say, the algorithm that started the new revolution in artificial intelligence. This is the algorithm that was used by DeepMind in 2015 to play in a superhuman way several Atari games. And maybe you heard this new, and that was at the end of 2015, just few months before AlphaGo came with completely different techniques. But Q-learning is, as of today, one of the best algorithms you can use for certain family of problems. How does it work? Well, it's very easy to understand if you followed me up to now. Look at this. I tried to put this in an algorithmic way. Start from time 0 and choose one action from your policy. Choose a behavior policy. Okay, a behavior policy can be an exploratory policy. The exploratory policy could be a uniform policy, for instance. You explore every action. Do this action and find the reward and the next state. Now, in the target, since you want to improve the target, for the bootstrap of the update target, use in part the target policy. That is, choose the action with the other policy. So you see, now we are not saying, if you compare with previous algorithm, previously I was saying choose this A from epsilon greedy. If you check Sarsa before, And here you had the same. You had choose A prime from epsilon greedy. From the same queue, I mean. You see, this was the same choice of the action. Now I'm allowing the algorithm to choose part of the target with another policy that can be greedy, for instance. I say part of the target because remember this part of the target comes because of the action A, and the action A is made with the exploratory policy. Also, the next state comes with the exploratory policy. So I just insert in the target this small correction that it is enough to make the algorithm give you the optimal policy. You see, this is the usual update rule in the language of target and error. This is the co-learning error, if you want. Co-learning error. And then iterate and go on. Okay, this kind of algorithm is giving you the optimal policy eventually, under a lot of other conditions that I'm not telling you, but just to get the idea. In this case, this is more clear, I guess. Now, no, wait, this one. Allora, in this case, this is the algorithm. Try following me here. Okay. Choose an action from a policy derived from the table Q. Okay, you have at the beginning a table of Q value, and we are updating these values. Okay, nothing new up to now. And now take the action and observe what happens, the reward and the next state. Now form the target. Can you tell me in this target where is the difference between the usual target? In this target, please point me out the part which is different from the usual target.
The maximum over all the actions.
Yes, this is new, right? What you should have normally in the Sarsa control part before?
Just having chosen one particular action from the policy and then evaluating it on that action.
Yes, and the one particular action was given in the Sarsa algorithm that was A prime chosen from epsilon greedy Q. Epsilon greedy Q. That is equal to this one. Okay, so before we were choosing the action in the same way as we were choosing the other actions. Now I'm choosing the action in a different way. You can say, but I'm not choosing an action here. I'm just taking the maximum value of the Q value. Yes, this is equivalent, if you think about it, in choosing the action equal to the argmax of Q, of QD as prime A, argmax over A. Is this clear? I'm choosing from the table the action which is giving me the maximum value. That means the greedy action, if you like. Greedy with respect to Q. And then I'm plugging this action here. And if you plug here the action that is giving you the maximum value of this table over all the action, then you get the maximum. Okay. So in this line, the improvement part is implicitly done by this max. And this means that we are using two different policies. One for choosing the most of the update part, the action in the beginning, the reward, the next state, and the state and the action here. But in one point, we are using another policy, a greedy policy, another family of policies, if you like to say so. The family of greedy policies from the tables Q. Okay. Now this algorithm is from 89, the original algorithm, and the convergence was proved 3 years later in 92. And the convergence result is this one. And I want to stress out the fact that in order to really state in a precise way such a theorem, you would need to be much more precise on how the algorithm works. How is I mean, this is stochastic control theory. You need to specify the dynamics of what you're doing. Okay, and as usual, we need the usual hypothesis, the same as before. We have, of course, already greedy in the limit because the policy is the greedy one, but we need infinite exploration, then learning rate in this L2, but not in L1. Okay, just to show you a graph, and then we can end. This is the difference between Sarsa and co-learning. I think this is very explanatory of the difference between the two methods. This is a grid world with a cliff. This cliff is a place where you can fall. If you enter one of these squares, then you go back to the starting state with a very, very bad reward, -100. And then you start again. You have to reach the goal, this square, with the least number of steps. And of course, the optimal path is this one, but this is very risky because if you are exploring, like Sarsa would do, Sarsa is exploring sometimes. So if Sarsa chooses this path, sometimes it will explore going south and it will enter the cliff. And this is very bad. For this reason, Sarsa, if you apply Sarsa algorithm to this problem, you observe that at the end, Sarsa will give you this path, which is safer. Okay, and which is not much longer, I must say. On the other side, co-learning, since it is also exploring, but the policy that is learning is the greedy policy, well, the exploration will give you a reward, a bad reward. Okay, so that will take the reward lower than the Sarsa reward, but the policy that will be formed at the end will be the optimal one. But you can see here from the reward, the co-learning from the reward perspective is worse than Sarsa, because the reason I just told you is falling into the cliff sometimes with the exploration part. And Sarsa, while Sarsa is choosing with the exploration and the epsilon greedy policy, which is the same, Sarsa has not the option of choosing two different policies for exploring and for learning. And so the policy will quite soon go to the safest path, and the reward will stay higher. Okay, in this case, if you are wondering which one of the two algorithms is better, well, it depends on the cost of falling into the cliff. If it is a simulated experience, then probably co-learning is better because you are learning the optimal policy. If you are making real experience, maybe the cliff is a real cliff on Mars where you have sent your spaceship and you are testing a robot and the robot costs 1 million euros, then probably you prefer the safer path instead of falling into the cliff. Okay, I would say we can stop here. There are two nice videos, but I prefer to stop and maybe answer some questions. Is there still somebody there?
Yes.
Yes.
Okay, while you think, if you have questions, this time I've given you a lot of exercises, and there are also hard encoding exercises because we have a lot of days. But I want to point out that of course we don't have time here in the talk of discussing the exercises. But if you want to try in doing this exercise, then you can contact me. We can discuss them. I mean, you can try solving them and send me the solution, but also not solving them. Just think about them, and we can discuss them in private. I mean, okay. I mean, these are hard in the sense that they are general. I'm asking you to prove the statement that I have given to you in the finite experience case that I was talking about. I'm asking you this. Each of these is a single research paper of the 90s, I guess. So these are in this sense, but one can try studying the paper, I mean.
Okay, if there are no questions, maybe we can thank Maurizio
for this lecture, and then we meet again next Wednesday.